All right, guys, section 2, chapter 10, simplifying radical expressions. So previously, a while back, we simplified radicals, just took the square root of something. Now, we're going to simplify radical expressions by using the product property of square roots and simplify radical expressions using the quotient property of square roots. So we have radical expression rationalizing the denominator and something called the conjugate. So the product property of square roots, a radical expression contains a radical such as a square root. Recall the expression under the radical sign is called the radicand. We talked about that in section 10.1. A radicand isn't in simplest form if the following three conditions, or is in simplest form, excuse me, if the following three conditions are true. 1, no radicands have perfect square factors other than 1. No radicands contain fractions. And no radicands appear in the denominator of a fraction. So the following property can be used to simplify square roots. It's the product property of square roots. Basically, underneath the radical symbol, you can break apart multiplication, is basically how that works. So here's an example. If I want to simplify square root of 80, 80 is not a perfect square, right? But if you get its prime factorization, you have 2 times 2 times 2 times 2 times 5 is 80. Now, you could break that apart into 2 times 2, or 2 squared, times the square root of 2 times 2, or square root of 2 squared, times the square root of 5. Well, these two factors make a perfect square of 4, and these two factors make a perfect square of 4. So the square roots of those are 2 times 2, or 4. So square root of 80 simplifies to 4 square roots of 5. Okay, so you could think of 80 as 4 times 4 times 5. Okay, and if it's under the square root, then you could think of that as square root 4 times square root 4 times square root 5. Right, this square root of 4 becomes a 2, times that square root of 4 becomes a 2, times that square root of 5 stays square root 5. And then 2 times 2 is 4, and that's how they got there. Okay? All right, here's a couple for you to try. Go ahead and pause the video. Okay, we're back. What you get? Okay, so 54, if I break apart 54, okay, 54 is 27 times 2. 27 is 3 times 9. And 9 is 3 times 3. So square root of 54 is square root of 2 times 3 times 3 times 3. Okay? Which I can write as square root of 2 times square root of 3 squared times square root of 3. And this square root of 3 squared is like really the square root of 9, so that becomes 3 times the square root of 2 times the square root of 3, which would be 3 times the square root of 6. Okay? That's the prime factorization way. Another way to do that is to realize that 54 is 9 times 6. And 9 is a perfect square factor. Okay, so normally when you're doing these, you're looking for perfect square factors. Okay, and I know that 9 times 6 is 54. So the square root of 54 is the square root of 9 times 6, which is square root of 9 times square root of 6, or 3 square root of 6. That's the final answer. Okay? Square root of 180, similarly, you could break it apart into 180 is equal to 2 times 90. 90 is 2 times 45. Oops. 45 is 3 times 15. And 15 is 3 times 5. So 80 is 2 times 2 times 3 times 3 times 5. So if that's all under the square root, I have square root of 2 squared times square root of 3 squared times square root of 5, which would give me 2 times 3 square root of 5, or 6 square roots of 5. Pretty cool, huh? Okay. Another thing you could do is look for perfect square factors of 180. So you might notice that 180 is 9 times 20. So 180 is equal to 9 times 20. So if I took the square roots of those, that would give me 3 square roots of 20. But 20 has a factor of 4 in it, so it'd be 3 square root 4 times 5. And 4 times 5, the square root of 4 is 2. So this would end up being 3 times 2 square roots of 5, or 6 square root 5. Same answer. Okay, you should get it. No matter which way you do the problem, you should get 6 square roots of 5. Shouldn't matter. Okay, just showing you different approaches there. Okay. All right, multiplying square roots. If I want to simplify square root of 2 times square root of 14, watch what happens. You can multiply those together, but 14 can be broken up as 2 times 7. So I could have square root 2 times square root 7. And then these two square roots multiplied to a perfect square factor of 2 squared 4, and that would simplify to 2 square root 7. Another way to do that problem is to multiply the 2 and the 14 together. If you multiply square roots, you can multiply the radicands together, and that gives you 28. And then you might be able to see that 28 is 4 times 7. Okay, and square root of 4 is 2, and square root of 7, 7's on a perfect square. So that's another way to get to the answer there. Okay. All right, here's a couple for you to try. Go ahead and pause the video. Okay, we're back. So 2a, 10 is square root 5 times square root 2. So this is square root 5 squared times square root 2, which gives you 5 square roots of 2. All right, the other way to do that one is to multiply it straight together. 50, or 5 times 10 is 50. And then you might be able to realize that 50 is 25 times 2. And the square root of 25 is 5, so it's 5 square root of 2. Okay? All right, square root of 6, square root of 8. So that would be square root of 2 times square root of 3 times square root of 2 times square root of 2 times square root of 2. And if I rearrange them, I would have square root of 2 squared. That takes care of those two. Square root of 2 squared. That takes care of those two. Square root of 3, which give you 2 times square root of 3. So you end up with 4 square root of 3. All right? Or you could multiply the 6 and 8 and get square root of 48. Okay? And one thing you could do is see that 48 is 4 times 12. And then that would be 2 square root of 12. But then 12 itself is 4 times 3. So you get 2 times the square root of 3, which gives you 4 square roots of 3. Or, right from the beginning, you might see that 48 is square root, or is 16 times 3. And the square root of 16 is 4, so that would simplify to 4 square root of 3. Okay? Again, multiple solution paths to the same answer, and basically all we're doing is just simplifying in a different order. Okay? All right, now here we got to talk about something that gets a little bit complicated, but pay attention, and it's pretty simple. It could just get a little bit complicated. So remember the expression square root of x squared. It may seem that x is the same as the square root of x squared because square and square root cancel each other. But when finding the principal square root of an expression containing variables, you have to be sure that the result is not negative. So for example, consider x equals -3. Does the square root of x squared equal x if x is -3? So let's see, let's replace x with -3. Now if I square -3, you get 9, and the square root of 9 is 3, not -3, okay? Because whenever you just have square root of x, that means the principal root. That means take the positive root. So if I have square root of 16, that's 4. I know previously we talked in chapter 9 that when you solve an equation and you take a square root, you have to account for the plus or minus. But we're not solving equations here. We're just simplifying expressions. And when you simplify expressions, if it's just square root, that implies that you just want the positive square root. okay? So notice in this case, if the right-hand side of the equation were absolute value of x, the equation would be true. So for expressions where the exponent of the variable inside a radical is even and the simplified exponent is odd, you must use absolute value. So if I have the square root of x squared, that simplifies to just x, so that needs the absolute value. If I have the square root of x cubed, that would simplify to x square root x, and you don't need an absolute value. If I have the square root of x to the fourth, that simplifies to x squared, because x to the fourth is x squared times the square root of x squared, which will give you x times x, which is x squared. So it wouldn't matter if x was positive or negative, because you're squaring it, you're going to get a positive. Okay, so you have an even exponent in the radical. It simplifies to an even exponent, so you don't need the absolute value. If I had square root of x to the sixth, then you'd need an absolute value, because the square root of x to the sixth simplifies to x to the third. So you had an even exponent simplifying to an odd exponent when you took the square root. Therefore, you need the absolute values. Okay? All right. So let's simplify the square root of 90, x cubed y to the fourth, z to the fifth. Okay, so 90, if I get its prime factorization, is 2 times 3 squared times 5. And then I have x cubed y to the fourth, z to the fifth. Now you could break that all apart and get square root of 2 times square root of 3 squared times square root of 5. The x cubed, I can break apart its perfect square factors of the square root of x squared and square root of x. X to the, or y to the fourth is a perfect square, so I keep it as y to the fourth. Z to the fifth, I could break apart its perfect square factors as z to the fourth, which is a perfect square, times the square root of z. So the square root of 2 is not a perfect square, so it stays. Square root of 3 squared is 3. Square root of 5 stays. Square root of x squared is just x. This came from x cubed, which simplifies to x square root of x. Okay, so you don't need the absolute value because the original exponent was not even. Okay, square root of y to the fourth simplifies to y squared, and z to the fourth simplifies to z squared and square root z. So what's that all simplify to? 3y squared z squared x times 10x times the square root of 10xz. All right, here's a couple for you to try. Go ahead and pause the video. Okay, we're back. So 32, you could think of this whole thing. This is how I like to do them. I like to think of 32 as 16 times 2, because that's the largest perfect square factor that I can get. And r is r squared. K to the fourth is k squared times k squared. And t to the fifth is t squared times t squared times t. So the square root of 16 gives you 4. Square root of 2. R squared gives you just r. Now, here's where you do need the absolute value, because you had an even exponent. When you square rooted, it became an odd exponent. Okay? K squared, the square root of that is just k times another k times a t times a t times the square root of t. Okay, now if I put that all together, I would have 4 absolute value of r, k squared, t squared, square root of 2t. Okay, so I put the 4, the absolute value of r, the k times k, the t times t all together, and then the square root 2 and square root t multiply together to give you 2 square root t. Okay. Now 56, square root of 56, x, y to the 10th, z to the 5th. I could think of that as 4 times 14, x, y squared, y squared, y squared, y squared, z squared, z squared, z. Okay, looks like people are sleeping there with all those z's. Okay, so that'd be 2 square root 14 square root x Then you'd have y times y times y. I forgot another factor of y squared in there. Times y times y times z times z square root of z. Okay? So this would simplify to 2y to the 5th z squared square root 14z. Now, you have to check. Did you have any even exponents that simplified to odd exponents? If you did, you need absolute value around that. Well, I had y to the 10th, simplified to y to the 5th. So even exponent simplified to an odd, need the absolute value around it. Okie doke? All right. That's it for this video. Let's stay tuned for the next one.